Hello, welcome back to AE 3530, System Dynamics and Vibrations. In this video, we're going to continue solving our example for a system with rigid body modes. There was some confusion last time about the initial conditions, so we're going to backtrack and redo that part to try and resolve that confusion. So just to recap where we are here, we previously we started off with our equation of motion. With the matrix form, we went and solved and computed the natural frequencies and the mode shapes. We then mass orthonormalized those and created the modal matrix. We then went and defined modal coordinates and used them to decouple the equations of motion. And by doing so, we end up decoupling them and finding a set of two equations for I equals 0 and equals 1 of this single degree of freedom harmonic oscillator equation, or second order ODE. We then want to go and compute the initial conditions. So for this system, our initial conditions are going to be, we'll have x of 0. This is going to be equal to x1 of 0, x1 of 0, x2 of 0. And we're going to set this equal to some constants. We'll just say x1, 0, x2, 0, and these are just some arbitrary constants. We can do the same thing for the initial velocity. X of 0 will be equal to x1 dot of 0. I'm going to run out of space here, so let me go ahead and I'm just going to reduce the size of this just to give myself some more space. Drag this on over. We'll rewrite this. We're going to have here x1 dot of 0, x2 dot of 0, and we're going to say that this is equal to v1 0 and v2 0, and those are just constants here. So if we go and apply our modal transformation to the initial conditions shown right here and right here, if we go and we apply this, we're going to end up finding the following. We will find that eta of 0 is going to be equal to the square root of m over 2 times the vector x1 0 plus x2 0, and then x1 0 minus x2 0. That's our initial modal displacements. We'll get the same thing for the modal velocities or modal speeds. Eta dot of 0 is going to be equal to, well, not the same thing, but we'll get something similar. It's going to be the square root of m over 2 times the vector v1 0 minus v2 0, or that should be plus in the numerator up there, and then below that we're going to get v1 0 minus v2 0. And again, these values are coming from our initial conditions that we listed up here for the physical coordinates. Now, keep in mind, and let me go ahead, I'm going to move this over just to add a little bit more detail here. So this is equal to eta 0 of 0 and eta 1 of 0. And this here is equal to eta 0 dot at 0 and eta 1 dot of 0. So those are our initial conditions. So each entry in the column represents an initial condition for one of the modes. We now want to solve each of these equations, each modal equation, and then plug in our initial conditions. So for the first mode, we're going to have I equal to 0, and we're going to get here eta 0 del dot plus omega 0 squared eta 0 equal to 0. That is the equation of motion. The initial condition, eta 0 of 0, is going to be equal to the square root of m over 2 times x1 0 plus x2 0. We're going to call this q0. Just while we work with this, or actually let's call this, we're going to call this, we'll call it P0, And then for the initial velocity, x eta 0 dot of 0, this is going to be equal to the square root of m over 2 times v10 plus v20, which we're going to say is q0. We'll come back and we'll plug in what these are later on. Okay, so we know that omega I, or omega 0 here is equal to 0. Whoops. And as a result, we're going to end up with eta 0 double dot plus 0 squared times eta 0 is equal to 0. So of course the second term is going to go to 0. And then we're going to be left with here that eta double dot of 0 is equal to 0. From here we can integrate both sides, and we're going to get eta 0 dot is equal to some constant. That constant is going to be equal to our initial condition, q0, which is then equal to the square root of m over 2 times the quantity v01 plus v20. We can integrate that again, and we'll get here that eta 0 of t will be equal to q0t plus p0 equal to, we pull out the square root of m over 2 times the quantity v10 plus v20 t plus x10 plus x20. And that is our solution. So we find here that eta 0 of t is equal to square root, all right, let me rewrite that, square root m over 2 times the quantity v10 plus v20 times t plus x10 plus x20. And that is the solution for the motion of the first mode, which is our rigid body mode, or the 0th mode. Just going to move that down just a little bit. Okay. So what we're going to get here, I'm just going to drag it over a little bit more. So we're going to find that the RBM is going to cause the system to move horizontally for all time as a rigid body. It's going to move, both masses are going to move the same distance for all time, or at the same velocity. And if there is no initial velocity, then they're going to stay at their initial positions for all time, or the summation of them. So we can just say here the RBM causes the system to move horizontally for all time. This is what we call this rigid motion. All right, we can now go on and we can look at I equals 1 now. Put that a little bit higher. So this is going to be for our only flexible mode. And in this case, we're going to get eta 1 double dot plus omega 1 squared. Eta 1 equal to 0. That's our equation of motion. For our initial condition, we're going to have eta 1 of 0 equal to the square root of m over 2 times x10 minus x20. And eta 2, or whoops, this should be eta 1 dot of 0 is going to be equal to the square root of m over 2 times v10 minus v20. And just like above, for right now, we're going to, oops, I left the dot. We're going to move this over, and we're going to temporarily call this R0. And then we'll call this over here U0. And this is just for convenience right now. All right, so this is a single degree of freedom harmonic oscillator equation that we know how to solve. And the solution here is undamped. So the solution eta 1 of t is going to equal to, well, r0 cosine omega 1t plus u0 over omega 1 sine omega 1t. And then we can go in and we can plug in what those are, u0, r0, as well as omega 1. For right now, I'm just going to skip that right now, just because it adds a lot of extra writing for no real reason, and we'll plug them in later. Okay, so from here, now that we've solved for the solution of each mode, we now need to go and perform a modal superposition to form the final solution. And in order to do that, we're going to first say here that we're going to recall that x of t, our vector of displacement, is equal to phi times eta of t. And then this will give us, if we go ahead and you were to expand this out, you'll end up with phi 0, 1, that's the first component of the 0th mode, times q0t plus p0 plus phi 1, 1, that's the first component of the first mode, times r0 cosine omega 1t plus u0 over omega 1 times the sine of omega 1t. And then x2 of t will be equal to phi 02 times q0t plus p0 plus phi 12, that's the second component of the first mode shape, times the quantity r0 cosine omega 1t plus u0 over omega 1 times the sine of omega 1t. And with that written out, you can go and you can plug these in, plug everything we know in here, and you'll get the following solutions in the box down below. That's already included in your notes here. You end up with this solution shown down here. One correction way at the end there with the sine term. And let me get the laser point out. We're going to make a modification to this term, and we're going to make a modification to this term right here. So these should be here. This should be 2, 0. That should be a 2, 0 beneath it as well. Otherwise, this expression is correct. Okay, now I went ahead and I plotted the response of each mode on the left shown here. And you can see that for just some generic initial conditions, in this case I set the parameters, the stiffness to 100, the mass to 1, compute omega 1 there. I set the time up to a time of 1 second. And then I provided some initial conditions here. And from what you can see here is that the rigid body mode, this eta 0, it just increases in time. It behaves time-like, and its motion is just increasing forever in time. Whereas we look at our second mode here, this eta 1, or the first flexible mode, you can see that it is oscillating. And then the combination of these two gives rise to the displacement of each mass. So something I want to just point out, if we look at the initial condition of x1, and we take a look, and we'll find that it is satisfied in this total response, whereas the initial displacement of the second mass is also satisfied. All right, like always, the MATLAB code is included here, and if you want a copy of it, you can scan the QR code. Okay, with that in mind, we're now going to move on and switch to looking at multi-degree of freedom systems under harmonic excitation. All right, so we're going to consider an MDOF system under a complex harmonic excitation. And so our equation of motion, in this case, is going to be mx double dot plus our damping matrix cx dot plus kx equal to F times e to the j omega t, where here this F itself is a vector of forcing amplitudes. Meaning that we could have multiple forces acting across the system. Each mass in the system could have multiple forces acting on it. Just like we did with single degree of freedom, we're now going to seek a steady state solution in the form of our vector of displacements x is going to be equal to some vector of complex amplitudes, e to the j omega t. And here, again, this is a vector of complex amplitude. And what this means is that we've absorbed the phase shift into it. So the phase shift is captured in that complex vector of amplitudes. We can substitute in the steady state response into the equation of motion. We will end up with the following, that the quantity minus omega squared times the mass matrix M plus j omega c plus k times x e to the j omega t is equal to f e to the j omega t. You can eliminate the e to the j omega t, assuming there's only a single frequency. And then we're going to call this matrix inside the parentheses, we're just going to call that A, and we'll use that in a moment. In fact, actually, we can leave that alone. We don't need to call that A. I take that back. We don't really gain anything from calling it. Actually, no, I'm wrong. We are going to need this A. All right. So we can then write that x is going to be equal to minus omega squared m plus j omega c plus k. Oops, not squared. That quantity inverted, so the inverse of that multiplied by f, which we can say is A inverse f. Okay, so we should note that when we have no damping in the system and the forcing frequency is equal to a natural frequency, whatever that natural frequency is, it doesn't have to be the first or second, it can be any natural frequency. Whenever this is true, we are not going to be able to invert the matrix A because the determinant of minus omega squared m plus k will be equal to 0. And therefore, we will find that the response or the amplitude of that big X will go to infinity. So thus, we'll find that forcing at any natural frequency of the system will result in a resonance phenomena similar to what we saw in a single degree of freedom system, except that was at a single frequency. Now we find that this happens at every natural frequency in the system. And this means that for an MDOF system, and in fact, this doesn't actually make sense. Let me correct this. Let's change this to an n. So n is just the number of degrees of freedom here, rather than m, to prevent confusion with the mass matrix. So for an MDOF linear system, n resonances can occur. This is true for a linear system. For a nonlinear system, more resonances than degrees of freedom can occur, and that's not a discussion for here. For a linear MDOF system, we will have up to n resonances that occur at the n natural frequencies. All right, we're now going to go on and take a look at example 3 here. I'm going to scroll up. We are going to consider a 2-degree freedom system without any damping in it, and then I'll add some damping later, although we won't necessarily go through the math on how to solve it with damping, but we'll just show what it looks like with damping. For now, we're going to consider an undamped system, 2 masses coupled together. There's a single spring coupling them, and only the first mass is grounded. So this system won't have any rigid body modes in it. And then we're going to apply a force F1 sine of omega t to the first mass. And we're asked to compute the steady state response for the 2-degree of freedom system shown and plot the magnitude and the phase of each degree of freedom. All right, so for our solution, we're going to first off write out the matrix form of the equation of motion. In the very beginning of this section of notes, we actually covered what this looks like for an n degree of freedom system, so you can just follow those formulas. So for our mass matrix, we're going to have m1, 0, 0, m2. This will be multiplied by our vector of accelerations, x1 double dot, x2 double dot, plus we're going to have our stiffness matrix, K1 plus K2, minus K2, minus K2, K2. Let me write that a little bit better. This will be multiplied by our displacement vector, x1, x2, equal to our forcing vector, and here we'll have F1 sine omega t and 0 in the denominator. All right, to compute the steady state response, we are going to complexify and then come up, provide an ansatz for that steady state. So let's just say to compute the SS response, that's our steady state response, we complexify and let x of t be equal to big X times e to the j omega t. From here, we'll end up plugging this into our equation above, and we'll get that K1 plus K2 minus M1 omega squared up there, minus K2 here, minus K2 down here, and then K2 minus M2 omega squared. All of that multiplied by our amplitudes, x1, x2, is equal to, now will be equal to our complex amplitude F1, 0, and down here below. From here, we can do what we said before and solve for x1 and x2. We're going to skip the algebra, and I'll write that out for you. We'll get x1 here equal to, and it's a big fraction. In the numerator, we're going to get, actually we'll do the denominator first. We're going to get K1, quantity K1 plus K2 minus M1 omega squared. That multiplied by K2 minus M2 omega squared minus K2 squared. And then we need to extend this fraction symbol. In the numerator, we're going to end up with K2 minus M1 omega squared. All of that multiplied by F1. And I'm going to do x2 on the next page. x2 is going to be equal to another big fraction. We'll have the same thing in the denominator. So we're going to get K1 plus K2 minus M1 omega squared. And the quantity K2 minus M2 omega squared minus K2 squared. Now in the numerator here, we end up with only K2 times F1. All right, and so that is the solution to this example problem. And in fact, this is what I'd like you to submit for your classwork today. I'd like you to submit your completed solution to this example. What example number is it? To example 3. And then I've also, below this, I've gone ahead and I've plotted the response using MATLAB. And then after that, we'll look at what damping does, although we won't derive any equations for that. All right, so we can plug in these equations into MATLAB. and we can go and compute what the amplitude looks like for each of these masses. And by the way, this is what I've plotted here, is the amplitude of the response here. So what we can see is that at omega 1, the response of x1 blows up to infinity if you are approaching from the left, or from the left, you'll see that the response here blows up to infinity. If you are actually approaching from the right, it blows up to minus infinity here. The same thing happens at x2. It blows up to infinity from the left and minus infinity from the right. So absolutely the amplitude is going to blow up to infinity at the natural frequencies. And so that means if you force closer to natural frequency, you can get a very, very large response. And the same thing is true for the second natural frequency. For the first mass, it's going to blow up to either positive or minus infinity, and the same thing is true for the second degree of freedom. So forcing at resonance is going to lead to very large amplitudes that are then going to lead to things breaking in the real world. Okay, so the MATLAB code is given here, and if you want it, you can download it using the QR code. We're now going to take a look at what damping does. I'm not going to provide the code for this here because I've used what is known as, I've done system state space matrices, and we'll deal with that later in the class. But I just want to show you what happens with damping. So when we add damping, the amplitude at the resonance is going to be prevented from growing unbounded, which means more particularly is that as the damping increases, we're going to get lower and lower amplitudes. So as shown here, in this direction, we have increasing damping. So one thing to be aware is that in these plots, you end up with both what we call resonances and anti-resonances. So this point that I'm now drawing in green, this here is known as an anti-resonance, or also known as a zero. These other two peaks, here and here, we'll write them over here. These are known as the resonance peaks. Or we just say resonances, or they're also called poles when it comes to like control theory. And we'll deal with that, what poles and zeros later. So the key thing is that at an anti-resonance, you get a very, very low response. So if you want your system to survive for a very, very long time under forcing, then it needs to be forced near a zero. On the other hand, as you increase the damping in your system, while you reduce the amplitude of the resonance peaks, you also decrease the amplitude of the resonances, but the price you are paying is that you increase the amplitude of the zeros or the anti-resonances. However, the anti-resonances are still very weak, very low amplitude, and they're still reasonable, to force at. I'll also say that this is shown on a log scale, and so we're looking at very low amplitudes at these zeros or these anti-resonances. You can see what the phase looks like. We start with a phase of 0, and then once we get to the first natural frequency, we have a switching of pi, and then it goes back to somewhere at the 0, it switches back to a phase of 0, and then at omega 2, it switches back to a phase of pi and stays there for all time when the damping is weak. And then as the damping is larger, you perturb away from these values, as shown in the color curves. So in this case, this is the direction of increasing damping. And we can see a similar curve for right here. So one thing that I will note for the second degree of freedom is that here we don't have an anti-resonance occurring. And so what happens is that there's only two masses in the system. And so at the forcing location, you will have the maximum number of anti-resonances, meaning that if you force at degree of freedom 1 and you force at this anti-resonance frequency, you will get a near zero response. at that location. If we come and we take a look at the second degree of freedom, we can just draw a line from here. You'll see that we don't get a zero amplitude there. So it's only at that degree of freedom. Now, the mass that is being forced will have the most number of zeros appearing. The mass or the degree of freedom that is furthest away from the forcing location spatially will end up having the least amount of anti-resonance peaks or anti-resonances occurring in it. So in this case, that is the second mass, and as a result, we have no zeros appearing. But we still get a very large response at the natural frequencies. So this is true always. This is the direction of increasing damping. And the same thing with the phase here. In this case, it drops down to pi, and then there's no anti-resonance to bring it back up, and then it drops back down to 2 pi, or in this case, it's going to be wrapping around back to 0. And then this is the direction of increasing damping. Okay, we're now going to move on and we're going to cover the next topic, which focuses on undamped vibration absorbers, and then we'll deal with damped vibration absorbers after that. Okay. So vibration absorbers are mechanical devices that reduce or eliminate unwanted vibrations. They are generally, they consist of a mass and some type of stiffness that is attached to the primary system that needs protection from that vibration. Generally, the mass is much smaller compared to the system that you're attaching it to, such that you really want to transfer energy into it. But it depends on the system, because you can tune that properties of this vibration absorber, which we'll see soon. You can tune that to optimally damp out the vibrations. We're going to consider here a single degree of freedom system as shown as a primary system here, but your primary system can be any linear system. It doesn't have to be a discrete single degree of freedom system like we're showing here. You can implement vibration absorbers on flexible structures like aircraft wings, wherever you want to. If you've ever heard of like pendulum dampers in large tall buildings, that's an example of a vibration absorber. A lot of like electrical power cables will have little vibration absorbers installed on them as well. So these things pop up all over the place. And then I would say that the area of nonlinear vibration absorbers is a very active field of research, and a good portion of my research has focused on nonlinear vibration absorbers, more recently focusing on using impacts to mitigate motion in multiple directions simultaneously in the next generation commercial aircraft. Okay, so like I said, they can be applied to MDOF systems. We're just going to consider a SDOF system here. In this case, when you apply it to an MDOF system, a linear vibration absorber may be tuned to match a specific mode or the forcing frequency as needed. It depends on what you're trying to do. The key thing is that if you want to match a single mode, or a linear vibration absorber can really only mitigate a single mode at best. Or it needs to be tuned to mitigate that mode. But in the case of nonlinear vibration absorbers, these things can be used to mitigate the response of many modes simultaneously. And that's what my work is focused on, is how can you use these to mitigate many modes of vibration simultaneously in multiple directions as well often. Okay, we're going to first consider here the undamped case of this system, and then we will go through the damped case later. So in this case, our equations of motion are going to be m1 x double dot, that's x1 double dot, plus k1 x1 plus k2 times x1 minus x2 equal to F0 sine omega t. And then for the second equation, which is our vibration absorber, we're going to have M2 x2 double dot plus K2 x2 minus x1. And that's going to be equal to 0. This is very much like the case we just saw for that forcing condition. We're going to assume, in this case, a harmonic solution. In this case, we're going to leave it as general. And we're going to see xi of t now is equal to some amplitude, xi sine of omega t, true for I equals 1 comma 2. And then by assuming this, we can obtain the steady state solution of each mass, which I've just listed down here. This is the same result as what we just saw previously. The only difference now is that we're going to consider how does the introduction of this vibration absorber change the frequency content of the machine itself. So like I said, and then we're also interested in reducing the motion of x1 in this case. So we're primarily concerned with reducing the amplitude of the primary system, that's big X1. So our goal is to make big X1 have an amplitude of 0. And to do that, we need to make the numerator of equation 44 be set to 0. So this will end up giving us that omega squared here must be equal to K2 divided by M2. Or in other words, our natural frequency of our vibration absorber by itself should be equivalent to the forcing frequency of the machine. So if the machine operates near its resonance before installing the vibration absorber, then omega squared is going to be almost omega 1 squared, which is going to be equal to K1 over M1. And thus, if we design the absorber, or it should be designed such that omega squared here is equal to K2 over M2 equal to K1 over M1. So if we design our absorber such that it has this natural frequency, then the amplitude of vibration of the machine while operating at its original resonant frequency will be 0. All right, we're now going to define some quantities that will allow us to make some nice looking plots. First, we're going to say that delta st, this is going to be equal to F0 over K1. And we're going to say that omega 1 is equal to the square root of K1 over M1. That's our natural frequency of the primary system. And then we're going to say omega 2 here is equal to the square root of K2 over M2. We're going to say that's the natural frequency of the absorber. And by doing this, we can then rewrite equations 44 and 45 as the following here. And here we end up with ratios of the forcing frequency. Let me get the laser. First of all, we got the ratio of the displacement amplitude to the scaled forcing amplitude for each of the degrees of freedom. We also end up with frequency ratios of omega over omega 2 and omega over omega 1. And we can now, with this, we can now actually go and plot these, and we can do comparisons between the responses of the two masses. So here's a response for a mass ratio of 1 over 20. That means that the absorber has a mass that is only 1/20th of the primary system. And here we're considering the case where omega 1 and omega 2 are equal to each other. And so what happens is that the absorber ends up splitting the resonance of the primary system. It splits it from a single resonance into two resonant peaks away from it. And thus we get here what we call capital omega 1 and capital omega 2. And we're able to show that if we're forcing here at this frequency omega over omega 1, that's where our resonance would have been. Instead, now we're going to get a 0 amplitude response. And as long as we don't force anywhere near capital omega 1 or capital omega 2, we won't cause the system to enter into a resonance response. Okay, so we find that the installation of the absorber splits the single resonance into two resonances with the frequencies of capital omega 1, capital omega 2. The operating frequency omega must be kept away from these frequencies. And if not, then we're going to introduce resonance like I just discussed. So the values of capital omega 1 and capital omega 2 can be found by setting the denominator of equation 50 to 0. So our equation 50 up here, we find that, we set those to 0, and then you can find the following equation for these two natural frequencies. Even this formula was too much for me to write, and so from here on, a lot of the formulas are going to become very big and very heavy, and we're going to instead just take them from the source where I found them. Okay, so we see here that each of these ratios of natural frequencies is a function of the mass ratio and the ratio of the natural frequencies. And so we can plot the variations of these two natural frequencies as functions of this mass ratio. I'm going to have to zoom out for this, but you can see here how these guys vary based on their mass ratios. Meaning that if you know that you want to operate within a particular range, let's say you not only want to operate near the resonance frequency, but you want to operate around it as well, you can then design your absorber and its natural frequencies in a way that allows you to expand the range of where you want to operate. So if I scroll up a little bit here, so if you want to try and, we're trying to change the distance of this between these two new natural frequencies, we can do that by designing our absorber to maximize. So if we know that we want to operate from like here to here, or in this, give me one moment, we want to operate in this region, but this response is too high, what we can do is we can change our vibration absorber in order to widen the gap between these two new natural frequencies. Okay, that is the end of this lecture. In the next lecture, we are going to go and cover what happens when you have a damped vibration absorber.